This will now be on statistical power. And I'd like to start with a simple cartoon that probably will stick to your memory. So what you see on this cartoon is a number of researchers, as signified by the white lab coats, who look at small samples of an underlying phenomenon. And based on the sample they're looking at, they come to a very divergent conclusion, considering the underlying question to be a sphere, a fan, a wall, a rope, a tree, or a snake. For those of you who don't realize it yet, actually it's an elephant. And the reason I like this is it illustrates beautifully how a small sample size can be misleading. And power calculations are all about generating sample sizes that are adequate and less likely to mislead you. If sample size is too low, it can have multiple consequences, including a sampling error, that the small sample you're looking at, contrary to expectation, is not representative for the population you are interested in. And the example of the elephant illustrated that one. As well, if you're looking at something you can quantify, that a too small sample size has a higher risk of many false negatives and at least some false positives. And I would like to illustrate that with a real example. So when I teach statistics, all the participants of the course get a database of 1,335 real measured values, in this case from a clinical cohort, and each participant randomly picks two sets of 10 values each from this database. And then they calculate means of the two groups, the difference between them, and a p-value. And what you can see here is that in this random group of 10 values, means of the group differ a lot. And also within the two groups chosen by one person, there are major differences. And what you can see here, ranging in this case from +5 to -4. Of course, since all the data come from one and the same database, the mean difference approaches 0. But every single sample of 10 potentially could differ a lot, and the difference between the two groups could also vary a lot. Whether variability is similar in whatever parameter you are looking at is a different question, but in most cases, we don't know the variability. And even though there was clearly no real difference in the underlying population because we only had one group, in some cases, we got very, very low p-values. So a small sample in this case could have led to a false positive finding. Before getting into that in more detail, I just want to recapture the definition that is used for describing the errors. A type 1 error, also known as false positive, means that you conclude from analyzing a sample of data that there is a difference if none exists in the underlying population. The contrary is a type 2 error, which is also called a false negative, if you conclude from analyzing a sample of data that there is no difference if it exists in reality in the underlying population. And again, I want to illustrate this in a little cartoon that you probably will never again forget. This obviously is a false positive or a type 1 error, whereas this most likely is indeed a false negative or a type 2 error. So having talked about the errors that can happen if you inappropriately choose too small sample sizes, I can come to statistical power. In a simplified way, you can say statistical power is the probability to detect an effect as statistically significant in a sample if it is present in the underlying population. Or more formally, statistical power, also described as 1 minus beta, describes the probability to detect a difference at least as large as you have specified with a given sample size and data variability. Because the power is defined as 1 minus beta, an 80% power means the beta is 20%. The choice of power you are applying in your study or in your power calculation is arbitrary. It depends on the purpose of your study, or it should depend on the purpose of your study. At least 80% power is standard for clinical phase 3 studies, and as said this morning, knowledge-claiming research can be considered the non-clinical equivalent of a phase 3 study. What drives a high statistical power? It's 3 factors. It's a large effect size, a large sample size, and low variability. Low power primarily increases the risk of false negatives, but can also lead to false positives. I would like to illustrate that with an analogy. A child is sent to the basement to find a tool. After a while, she returns and says, "It's not there." Well, is the tool there or not? It depends. How long did she look? That's sample size. Is the tool as large as a snow shovel or as small as a tiny screwdriver? Effect size. And is your basement a real mess, as shown on this photo, or is it well organized? Variability. On Monday, you heard about the false discovery rate or the positive predicted value. And as one of the pre-reads, you hopefully have looked at the Ioannidis 2005 paper. And to illustrate my point, I'm just showing you one of the tables, and I want from that paper, I want you to focus only on these 2 rows because everything here is identical. The true to not true relationship is the same, 1 in 10. The bias factor is the same, but in one case, you have a power of 80% and in one of 20%. For a given p-value, the positive predictive value with high power would be 20%, but with low power, it would only be 12%. So the false discovery rate is indirectly a function of statistical power. How does it look? And I'm showing you here data from a paper from Catherine Button, and she looked at systematic reviews and meta-analysis published in 2011 in the Neurosciences, and based on the effect size or the estimates of the true effect emerging from the effect sizes and the reported sample size, she went back to the original studies to look at the question, how much power did they have in hindsight? Only 14%, that's 1 in 7 studies, had a power of more than 80%. And I told you, in clinical research in a phase 3 trials, This is the minimum power you typically have. Less than 30% had intermediate power, and 57% had a power of less than 30%. If you went for a clinical study to your ethical committee and described that you plan a major clinical study at a power of only 30%, they would just laugh at you. You would not go through the ethical committee with a so poorly powered study. Why is that? Well, actually, at least some in the room may remember the original Star Trek television series, where the engineer Scotty notoriously said, "We need more power." And that applies here as well. We had a discussion this morning, also the question whether an animal committee may be a limiting factor for research rigor, and appropriate power is clearly one of the possible effects in research rigor. For quite a while, several animal committees have argued if you want to have so many animals in your study, we consider that unethical because you put so many animals at potential harm. Well, you could make the exact opposite point by saying if the study is underpowered, all animals may unnecessarily be exposed to potential harm. So I'm showing you here an editorial from Nature from 2015 reporting that important funders such as the Wellcome Trust in the UK demand much stronger statistics for animal studies. I can tell you from my experience in the Netherlands that already for years and years, the law there mandates that if you want to run an animal study, you have to provide a power calculation-based sample size along with your study protocol in order to get your study approved. I hear that in Germany, it differs a lot by the regional or local jurisdiction, where some animal committees still think that too many studies is not good for an animal studies, whereas others feel that if you have too few animals, basically all the animals in the study are wasted. And that's an ongoing discussion. The question is, what do I need for a power calculation? Basically, there are four things which the power calculation is asking you for. What is the effect size you are looking for? And in this regard, it's not about the effect you expect. It's about the minimum effect you consider relevant. Second, how much variability do you expect? And then, what is the desired statistical significance level? In the language of a statistician, the statistical alpha. And how much power do you want? A power of 80% is almost as customary, at least for large clinical trials, as a p-value threshold of 0.05. But what you choose for your study should not be dictated by an automatism, but rather based on the question under investigation. And I'll be coming back to that in just a moment. The technical power calculation is the easy part. There are many freely available software tools, and one of them that is used very frequently, for example, is G-Power. However, the tricky part is defining the parameters that you enter into the mask of the software. As I said, what is the minimum effect size about? If I run a clinical study on a new drug to lower blood pressure, I know from numerous large studies from the past that at the population level, a lowering of 2 millimeters of mercury already leads to a relevant change in cardiovascular outcomes. However, for most non-clinical studies, I lack such knowledge. If, for example, the primary outcome parameter is the expression level of a certain enzyme at the mRNA level, in most cases, probably we have no clue how much of a change would be relevant biologically. The same applies for variability. Sometimes people take their estimate of variability from a small pilot study with just a handful of animals. But as I showed you with the initial picture of the elephant, the small sample size can be highly misleading. Thus, unless you have a lot of experience with a given assay, it's highly difficult to predict which variability you can expect. The much easier parts are determining statistical alpha and beta, and it's basically asking a question: how much of a risk of a false positive do I accept? The more risk you accept, the higher the p-value threshold can be, and the less risk you accept, the lower it must be. Which beta? Again, how much of a risk, especially of a type 2 error, do I accept? Imagine if the power is low, there may be a real effect that you don't detect, and therefore a promising research direction may be closed for the wrong reasons. Thus, the choice of alpha and beta depends on whether you are more afraid of type 1 or type 2 errors. The 0.05 and 0.8 that you so frequently see in the literature are not rules. They are just common habits. And what you need should depend on your specific question at hand. On this slide, you can see an example of a power statement, and I must admit I don't recall from which paper I picked that. It was a clinical paper. So they wrote, we chose to study 313 subjects in each group in order to have 80% power to detect a 33% reduction in the recurrence rate from a baseline rate of 30% with a significance level of 0.05 two-tailed. Well, that's a lot of words. What does it mean? For effect size, the investigators were looking for a 30% reduction in relative risk, and they said the baseline risk was 30%, so in absolute risk, they were looking for a reduction from 30 to 20%. They set the significance level, the statistical alpha, at 0.05. And for variability in this type, they were looking for proportions based on how far they were away from the expected baseline. And the power they set at 80%. With this, let me come back to the power calculation and the animal studies. What you see here are simulations for a certain type of assay with how many animals per group would you achieve how much power. And you can see, obviously, the more animals you have, the more power goes up. But you also see that you are rapidly coming into territory where you will have issues, for instance, with the budget of your study. However, you can turn up and say, if I have an underpowered study, the issue becomes that potentially all animals are wasted. So increasing the number of animals can also be seen as a measure to prevent wasting your animals. Let me come back to the consequences of poor power. Low statistical power reduces the chance of detecting a true effect, which means you have the type 2 error. It increases, on the other hand, the risk of false positive effects, the type 1 error. Even if you end up having the right answer, typically poor-powered studies overestimate effect sizes. As such, they are causes of a high false discovery rate and, following from that, a low reproducibility. You could also more pragmatically say that poorly powered studies waste animals time and money. They lower the robustness and predictive value of an animal study, and they may lead to inappropriately closing a promising research direction. If you listen to what I already said, you may wonder, well, why not power for 99%? And then in a perfect world, that of course would be the ideal situation. And I'm taking here data from a paper from one of the classic animal care professionals, the ALAC journal. What you can see here is, in this example, increasing number of animals by just 5 increases your power by 10%. That's a fairly big increase. On the other hand, as you have the relationship between sample size and power is an asymptotic curve. If you want to increase power from 95 to 99, so just 4 percentage points, you need 22 additional animals. Thus, the additional certainty you get by increasing power becomes disproportionately high if you're already here. And that also shows you why the 80% level has been used so often. This is approximately where the slope turns from steep into shallow. And at that point, the number of additional samples or animals or patients you need becomes disproportionate for any increase in power. I think this is a good point for a small excursion into technical versus biological replicates. As a biological replicate, I consider one animal from a group or all the cells from one. In this case, variability is a composite from the biological variability and the variability introduced by the measurement and detection related factors. In contrast, multiple samples or measurements from one animal or one plate constitute technical replicates. If you compare the technical replicates with each other, what you're doing is primarily addressing variability coming from measurement or detection. The mean or median of technical replicates increases the precision of assessment in the biological replicates. That is the value of having multiple technical replicates. Statistical analyses should always be based on biological replicates. And the main reason for that is any statistical test assumes that you're looking at independent samples, and technical replicates are not independent samples. Funny enough, Just this morning, I came across a paper published 2 days ago that beautifully illustrates this problem. It's based on modeling, and they looked data from 3 hypothetical animals per group with 5 cells, technical replicates measuring in each sample. If you do the mean of each quintuplicate and take this as your biological replicates, you have a study with a fairly low sample size. And even though the difference between groups looks large, the p-value is high. If you would wrongly treat each technical replicate as independent in the statistical analysis based on your new n is 15, even though the data are exactly the same, you suddenly get a p-value of 0.0007. This looks very tempting, but it is wrong. What you have done here ultimately is you created pseudo replicates and a pseudo increase in sample size. I told you, power depends on sample size, variability, and effect size. If what you're doing is not really increasing sample size, but just a pseudo increase, you may get a low p-value, but this low p-value is misleading. Another excursion, and that applies mostly to in vitro work. Let's assume you have done 6 experiments, observed an effect that you found interesting, and calculated a p-value of 0.06. That sucks. On the one hand, the effect is so large and interesting that you really want to push for it. On the other hand, at a p-value of 0.06, you can neither conclude you really have found that, nor can you conclude you have found that there is no difference. Common practice has been for a long time, and I'm happy to admit I've done so too in the long distant past, just do 2 more experiments. This is wrong for 2 reasons. Number 1, a principal assumption of all statistical tests is that you are looking at a random sample. However, your new n is 8 is no longer a random sample because it was spiked by the n is 6 you liked. If it's no longer a random sample, there no longer can be meaningful statistical hypothesis testing. But there is also a second reason why this is wrong. Actually, you now have done 2 statistical comparisons, one of the n is 6 and one of the n is 8. If you would ignore the first argument, still, if you are doing 2 comparisons, you must apply a multiple comparison adjustment, just as you would do with any other multiple comparisons. So what are the possible options you have if you have this interesting finding with a p-value higher than you like? Well, you could either say, I report the data as they are with the group difference and its confidence interval, which most likely then will overlap, because the definition of overlapping confidence intervals is that the p-value must be greater than 0.05. If the finding is really interesting, however, I recommend a different approach. Consider this experiment exploratory and repeat it, most likely with a larger sample size. So not adding 2, but doing, for example, a whole set of 8 new experiments under knowledge claiming research conditions, and then report both. And then reporting the original exploratory finding may make the KCR finding even more relevant, because you can now say, actually, the finding was consistent across 2 studies. Can I do a meaningful power or sample size calculations? As I said, this really for me is a key point. That's why I'm repeating it already for the 3rd time, this presentation. Very often in experimental biology, we lack meaningful a priori knowledge on what is a meaningful biological effect size and which variability I can expect. Lack of such knowledge reduces the relevance of power and sample size calculations. Of course, you can do it technically, but the numbers you get are no longer really relevant, which means that often guesswork is required in pre-specifying sample sizes. In my opinion, a preset best guess sample size in almost all cases is better than an adaptive sample size. Can you afford the necessary power? If the power calculation tells you you need 97 animals per group, and you go with that first to your supervisor, he will tell you, are you out of your fucking mind? I don't have the money for that. And even if he or she has, if you go to the animal committee, they may say, are you out of your mind? Because this is a very, very big study. You can ask a counter question. Can you afford to perform an underpowered study where the entire study may end up being irrelevant? Remember, a poorly powered study is likely to yield a non-reproducible result. It's likely to waste all the animals involved. In contrast, a properly powered study uses a lot of animals, but it may be worthwhile. And coming to my final slide, how can I deal with this pragmatically? One thing that many people don't realize, you markedly can increase power by reducing variability rather than increasing sample size. That can be done, for instance, by fine-tuning methods and/or adding technical replicates. There is a rule of thumb that many will find surprising. If you can bring down variability by 50%, mathematically, it's the same as increasing sample size by a factor of 4. So it may be very helpful to spend a little time on refining your methods and approaches to bring down variability. Alternatively, you could ask, what can I learn with reasonable power from the sample size that I can afford? Perhaps you should not run an experiment that you cannot pay for once it's adequately powered. And with pay for, I do not necessarily money, but all the resources involved. Whatever you do, sample size should be defined prior to starting the power. And if all of that sounds somewhat frustrating, I would like to remember you of an old song from the Rolling Stones. Again, some of you may be too young to remember this. You can't always get what you want.